Hey everyone, we're about to dive deep into one of the most mind-bending questions you can possibly ask. What is nothing? Because it turns out that at the very smallest scales of reality, the answer is, well, it's a lot weirder and honestly a lot more crowded than you could ever imagine.
So let me just start by asking you this. What if the vacuum, that perfect, absolute emptiness we all picture, what if it's actually a seething, chaotic, buzzing sea of energy? And look, that's not some sci-fi concept. That's the actual reality described by quantum mechanics. All right, so first things first, we've got to completely dismantle our everyday idea of what a vacuum is. We're going to peel back the curtain on the void and discover this hidden energy that's just humming away right beneath the surface of reality. This is such a great way to picture it. Don't think of empty space as some silent, still, boring box. Instead, imagine a perfectly calm ocean. Now, at the quantum level, this ocean is just constantly erupting with these tiny, fleeting waves of energy. Those are quantum fluctuations. And yeah, this slide just lays out the difference perfectly. The idea we all grew up with, that's the classical vacuum on the left, just nothing, zilch. But the quantum reality on the right, whoa, it's this dynamic, bubbling foam where bits of energy and matter can literally just pop into existence for impossibly brief moments. So how in the world is that possible, right? How can something just appear from absolutely nothing? Well, it's not magic. It all comes down to one of the most fundamental rules of quantum physics, a principle that basically lets reality take out a very short-term loan. And here it is, the core concept. A quantum fluctuation is just a little temporary hiccup, a random blip in the energy at one specific point in space. But here's the crucial part. This isn't just some wild guess. It's a direct consequence of a fundamental law of the universe, the uncertainty principle. So, Heisenberg's uncertainty principle is the cosmic loophole that makes this all happen. To put it simply, it says there's a hard limit to how precisely you can know a system's energy over a certain amount of time. So for an incredibly brief instant, that uncertainty allows a tiny bit of energy to be borrowed from the vacuum. And just like that, you can get something from nothing. And this is exactly what happens with that borrowed energy. It's a three-step dance. 1, the energy is borrowed. 2, it instantly converts into a pair of virtual particles, like an electron and its antimatter twin, a positron. And 3, before the universe can even notice the loan is overdue, they slam into each other, annihilate, and repay the energy debt. They just flicker in and out of existence in a flash. Okay, this all sounds like a pretty wild theory. I mean, virtual particles that exist for a fraction of a second, how on earth could we ever prove they're actually real? Well, let's get into the evidence, because this is where it all becomes a concrete, measurable reality. You see, this is not just some mathematical fantasy. We have hard experimental proof. Things like the Lamb shift in hydrogen atoms, the famous Casimir effect, the very mechanism that powers Hawking radiation, even mind-blowing measurements from the LIGO Gravitational Wave Observatory. They all point to the same conclusion. The quantum vacuum is real, and it has very real effects. Let's just zoom in on one of the most direct proofs we have, the Casimir effect. The theory is wild. It says if you take two perfectly flat plates and put them incredibly close together, a real physical force will actually emerge from the empty space and push them together. And when I say close, I mean really close. We're talking less than 1,000 nanometers apart. At that tiny scale, it turns out more quantum waves can exist on the outside of the plates than can fit in between them. This creates an imbalance, right? A net pressure from the vacuum itself that physically shoves the plates together. It's a measurable force created from nothing. Incredible. Now, if you think a tiny force on tiny plates is cool, get a load of this. In 2020, scientists at LIGO, the observatory built to detect ripples in spacetime, they confirmed that their massive 40-kilogram mirrors were actually being subtly jiggled by quantum fluctuations. This took the effect from the world of the nanoscale straight to the human scale. A truly amazing confirmation. And here's where it gets really mind-blowing. These tiny, little flickers of energy aren't just some microscopic curiosity. No, they have huge consequences for the largest things in our universe. They influence everything from how black holes die to the ultimate fate of the entire cosmos. So, take Hawking radiation. Picture one of those virtual particle pairs popping into existence right on the edge of a black hole's event horizon. Now, what if one particle falls in, but the other one manages to escape? Uh-oh. They can't annihilate each other anymore. The one that got away becomes a real particle, carrying energy away from the black hole. This process literally causes the black hole to evaporate, incredibly, incredibly slowly, over trillions of years. But, and this is a huge but, this leads to one of the biggest paradoxes in all of physics. See, if the vacuum is so full of energy, it should have a gravitational pull, a massive one. So huge, in fact, that it basically breaks our understanding of the cosmos and makes us ask, why is there even a universe here at all? So, according to our best quantum theories, the amount of energy packed into a single cubic meter of empty space should be this. That's a 1 followed by 113 zeros. I mean, just try to wrap your head around that number. It's so big that if it were true, the universe should have blown itself to bits an instant after the Big Bang. But when astronomers actually go and measure the energy of the vacuum by looking at how the universe is expanding, they find this number instead. It's tiny, practically zero. That gap between the absurdly huge prediction and the minuscule observation is known as the vacuum catastrophe, and it is, without a doubt, the single largest disagreement between theory and reality in the entire history of science. And right now, nobody knows how to solve it. But even with these giant mysteries, scientists aren't just standing around scratching their heads. They're actually learning to control the quantum vacuum. We are now at the frontier, moving from just observing this bizarre feature of reality to actively trying to manipulate it. And the progress is happening lightning fast. Like we said, 2020 gave us that incredible LIGO discovery. Then, just last year, a team at MIT proved they could use a weak laser to sort of nudge these quantum fluctuations, controlling their randomness. And looking ahead, new super powerful computer models are being built to simulate these complex interactions in full 3D. And you can really feel the excitement in this quote from one of the lead researchers. This isn't just some abstract academic exercise. Think about it. If we can gain control over the most fundamental randomness in the entire universe, that opens up completely new doors for things like quantum computing, ultra-precise sensors, and technologies we probably can't even dream of yet. So where does all this leave us? We started off thinking of empty space as simple, boring nothingness. And we've ended up with this chaotic, energy-filled landscape that can jiggle huge mirrors, make black holes evaporate, and might one day be something we can actually control. It just leaves you with this one final fascinating thought. If the simple concept of nothing turned out to be this full of secrets, what other profound truths about our universe are we just completely overlooking every single day?